And BERT paper. Honestly, if you Google BERT paper, it's the first one that comes up on
Yeah.
ARCS. How do you even pronounce that? ARCS IV? ARCSIV?
Oryx? Oryx?
ARCS?
I
Anyway.
don't know.
Okay. Uh, I. Here, let me see. Your entire screen share. Oh, cool. There was an error. Let me leave and come back.
All right.
Your entire. Sure. Man, Macs are so annoying. I can't like. All right, hold on. Maybe tabs. Maybe I can share a tab. Can you see this tab?
Yes.
Oh, cool. Okay, so tab sharing
Oh,
works a lot better than
yeah.
screen sharing. Okay. So I guess let's get started. I wasn't super happy with my presentation of attention is all you need. And I think mainly it was because I didn't understand NLP very much, so I had to go back to like RNNs and LSTMs and stuff to get a conceptual understanding of everything. So
Yeah.
I want to take a step back. Luckily, BERT is actually really simple once you really
Mhm.
understand specifically the encoder of a transformer architecture. So I wanted to take a step back, really hammer through the attention mechanism, and then talk about BERT and what it does and all that stuff. Yeah. So
I'm gonna dinner, so in the background, so I'll just mute myself. But yeah,
okay.
continue.
Yeah. Let me know. You can feel free to interrupt if you have any questions. So BERT is essentially so the classic transformer architecture from Attention is All You Need. BERT is the encoder portion of the architecture stacked on top of each other sequentially. So you can think of that as taking the input, embedding it based on attention between words within an input, and then doing that attention multiple times. And we'll talk about what an attention block is and what that practically means. But essentially, if you really want to have like a high level conceptual understanding, you have a word by embedding dimension tensor, right? So there is a row for every word and a column for every um, dimension in an embedding. And that maintains throughout these blocks, except the embedding becomes more and more complex. It embeds on the embedding on the embedding on the embedding. So we'll talk through like the tensor flow. But generally, the idea is you stack these transformers or these encoders on top of each other, and then you have some.
Wait,
Sorry.
just a second. On the left, so this is still bird on the left, right? Like the most left picture.
So this is an encoder. This is from the classic attention is all you need encoder decoder architecture. So this encoder, really kind of besides some of this stuff, but this encoder, the multi-headed self-attention, technically masked multi-headed self-attention, I'll get to that. But this transformer encoder is stacked on top of each other. So you have
Yeah. I just saw a thing that I have not paid attention to previously. Are those skip connections between like multi-attention head and feed forward?
They are, and I'll get to the flow through the attention mechanism. So we'll really hammer through this block and everything that goes into it. But like right now, just really high level, you have this multi-headed self-attention, which happens multiple times, and then that is BERT, right? So keeping a really high level for now. Uh, Basically, the idea of BERT is that it's a language model. So it's not really. So the term language model is kind of interesting because I think I always thought of multiple things as language models, but language models are for one, understanding language, and generally text completion. That is what a language model is. So the objective of BERT really is to be a model that has a general understanding of language, that then different models can be applied to it and fine-tuned for specific tasks. So with BERT, you have this input sequence, and then you have this stacked multi-headed attention encoder, which is this big blue BERT block. And then you have a variety of outputs, actually. You have one that's specifically for um, if I'll get to this, but you have a few different outputs that are used for different types of training to entice these encoders to have a general understanding of knowledge, and then this can be fine tuned using different outputs for specific tasks. Does that generally make sense?
Yeah.
Okay, cool. So yeah, that's the idea. So before we really go into BERT and fine tuning and how it's trained and all that stuff, because really that's what's interesting about BERT specifically. But I think it's really important to have a general understanding of multi-headed self-attention and the things around it. So really briefly, the words go through a word embedding. We know it. There's word to vect. There's another one that BERT uses. They're all over the shop. They match a one hot encoded word or maybe integer or whatever into a vector that represents that word. So I went on this a little too much because I thought it was really interesting. We talked about how this is kind of similar to a motor encoder, which I thought was really cool. But actually, the positional encoder is not actually used in BERT. In the attention is all you need paper, they talk about how you can use functional positional encoding using sine and cosines, or you can use learned positional encodings, and that they're fundamentally similar. I suspect the reason BERT uses learned encodings is because of some of the intricacies of how it's trained, but conceptually it's the same. BERT uses a learned encoding instead of a sine and cosine wave, but you still have this positional encoding idea, right? So that's the input, right? You have a series of words that get embedded into a word vector space, and then you have some sort of positional information that's applied to them. So now you have a tensor, right? So now this goes to the encoder block, right? So kind of critically, if we think of the encoder as a black box, the idea is you have a tensor, which is sentence length by embedding by batch size. And then you get the same tensor size back, which is, sentence size by embedding size by batch size, except the values within the tensor reflect some sort of relationship between words within the original tensor. So that's the point of multi-headed self-attention. It's to add inter-word context and inter-word understanding, right? Let me, real quick, no one else is trying to meet. All right, cool. So how is this done? So I found this really fantastic example that breaks down the multi-headed self-attention into a series of tensors and their operations, and we'll go through one by one. So the first thing that happens is your input, which is so you have the vector embedding, then the positional encoding, and then you have, your tensor, right? So that's the sort of vector embedded positional whatever. This goes through a feed forward network, and it creates essentially three versions of the same tensor, which is the query, the key, and the value. So this is, technically speaking, this is concatenated together, but you can think of these as three separate tensors. So you have the, the sequence length dimension on this side. You have the batch size as the depth, and then this is the embedding for the query. This is the embedding for the key. This is the embedding for the value, right? So, so attention, which we've talked about, you can. I didn't. I was gonna dig really into why it's called query, key, and value. I think the reason there's query, key, and value is because it relates to attention, which relates to other disciplines. But really, the query and key are functionally very similar. We'll kind of, I'll go through the intention mechanism, and maybe we'll talk a little bit about the query, key, and value. But anyway, so
I remember making notes on that. Towards the end, I can try to dig them up and see what they said.
Gotcha. Yeah. So I mean, based on what I've seen, in terms of transformer encoders, it kind of becomes a little wishy-washy. It's useful for a human's conceptualization of what's happening. You can think of it as switching. You can think of it as selection, but really it's more homogeneous than that. It's a little more loosey-goosey, I think, as far as the model's actually concerned. So we'll avoid the going too far into the terminology. But essentially, the idea is, so this query, so let's say we have eight attention layers. So this query tensor is subdivided 8 times. The key is subdivided 8 times, and the value is subdivided 8 times. And then each eighth is then provided to another, to a self-attention layer, which is why it's called multi-headed self-attention, right? Then, let me see. I wish I had some water. Okay. So it's kind of important to, I guess, wrap your brain around what this tensor looks like. So this is still the sequence length dimension vertically, but now you have subsections of the embedding. That's kind of how I think of it. I don't know if it's true. I'm pretty sure it's true, though. So you take the embedding dimension, and you subdivide it 8 times, and you split up the embedding across these multi-headed attentions. And I think the idea of it is you can get different types of attention in different kind of regions of the embedding, if that makes sense. So the query, key, and value, basically the query and key are multiplied together, via a dot product cross product. I think that's a cross product, right? Anyway, the one with the matrices. It's funny, I haven't taken linear algebra in forever. But you get this sort of association matrix. And actually, I think I have a practical example over here. So I won't go too far into, I didn't make one for that. Let's see my notes, because I don't want to skip any concepts. Okay, yeah. Yes. So I'm trying to recall the nature of a cross product, because it is really important to oh man, this is a point that I maybe should have hammered a little more home onto. Why does doing a cross product to make this really matter? Like conceptually, the hand wavy example is it is a relationship between a word and the same word, or a word and different words, right? So it's like you have all of the words in the sequence and all of the words in the sequence, and it's how much a word relates to another word. That quote unquote relates. I'm not actually sure on the math. It should be really easy to build a mathematical bridge to that level of understanding just by reviewing the cross product, though. I can't, I would have to run through a few examples.
So yeah, so the way that I think, when I learned it the first time, I was reading about it the first time, the way that I understood it, right, is essentially a dot product um, of like certain type of matrices will be a projection. And you remember how kind of in kind of word embedding, we essentially embed words in a vector, and they give you an example that, like, in a way that, for example, king minus I think it was man will be equal to queen, right?
Yeah.
They gave something like that. So if you flip this idea, if you have them sort of encoded vectors on these kind of like, you can view so the way that you could also view king minus kind of woman would be vector of king projected onto the plane of all of the objects women related. And the way that I understand kind of the key and why it's kind of multiplied again with the value is that essentially it's projecting onto certain planes, and across these planes it searches for the distance of these vectors. So in a way, you kind of project, let's say, all of the vectors now into, I don't know, everything French related, and you search whether on the plane of Frenchiness, are there any words kind of close to each other in this plane?
Mm-hmm. Okay, that makes sense. I think I need to learn a little more about this to, I think, really be able to explain it super well. It's so funny. It's easy to take things for granted. You know, you just go like, oh, you multiply them and then you're done, and you know, like, oh, I know how to do a cross product, and it's like, yeah, it's like the outside dimensions are and then they have to have the same. And so then you're like, whatever, and then you go to explain it, and you're like, wait a second, like, why does the cross product mean relationship? Like, why does that? So I think I need to review that a little bit. But regardless, I think the thing that's really important to kind of remember is that these query key and values are generated from a feed-forward network. So while it is the vector embeddings of this word versus this word, it's different embeddings of the same word given a learnable transformation, right? So the self-attention mechanism actually has no parameters at all. It's just what you define as the query key and value that ends up, resulting in the output, right? So this idea of finding the similarity between things, you can learn to adjust that similarity based on changing the definitions of the query and key, right? So I think that's super important conceptually. But so you build this sort of relationship matrix based on the query and key. Let's see. So padding or masking. I'm actually going to skip this a little bit because exactly how masking is done from model to model can kind of be a little weird. Sometimes when you're training, you take tokens that you're trying to predict on and you set their attention to like either 0 or negative infinity. And I think you decide to do this based on when you're inferencing and when you're training. So there's actually a lot of subtlety, which is application specific into the way that you're masking. But across different models, be it BERT, be it GPT, be it some other transformer-based model, the idea is when you're training, you can choose not to look at certain attentions that may give information you're not supposed to have, or may be problematic in some way. Like maybe you don't want to learn about the attentions that are related to service tokens like start, stop, mask, and whatever, right? So there's a variety of ways to do masking, but this is an important step, but it's kind of dependent on the model, right? So regardless, you do masking. You put it through a softmax, which, so I guess kind of curtailing on your definition or on your description of how it's sort of distance related. This takes, I guess, the relative distance of vectors and then turns them into essentially a probabilistic selection, right? So instead of like, you might be 4 units away from this vector and 3 units away from this vector and 6 units away from this vector, but the softmax squashes that to a sum of a range of 0 to 1. So essentially you're X% close to this vector, X% close to this vector, et cetera, right? And then you multiply this attention matrix by your value vector, and then the value vector is what is output of this attention mechanism. So let me see here. If I go back up a little bit, so we have 8 queries, 8 keys, 8 values. The query and key are used to make the sort of. It's funny. I don't know which one of these is actually called self-attention. I think it's this one. So use query and key to compute this sort of this distance matrix. You mask it, and then you apply a softmax to create the self-attention. You multiply that by the vector, and you get this output. And then you restack all 8 back together, and that is the output of the attention mechanism. So you still have the sequence length dimension by the embedding length, but now the values have changed significantly as a result of this self-attention sort of construct, right? So so then you have this little slice, they get concatenated together. And I kind of wanted to people kind of hand wave a lot of this stuff, but I went ahead and made my own little thing. So I have, let's see, I have 5 vectors, 5 words that have an embedding of size 2, right? And then this is the sort of attention mechanism that I arbitrarily made. And it respects softmax, right? So it's 1, 1, and I'm pretty sure I got the orientation right. It might be that it has to be softmax on the vertical direction instead of the horizontal direction. I'm not really sure, but I think conceptually it kind of displays the idea. So you have softmax, this is equal to 1, this is equal to 1, this is equal to 1. And if you kind of look at these numbers, it can kind of help you build an intuitive understanding of what's going on, right? Like this one is mostly itself and a little bit this one, which you can see. And this vector becomes mostly itself, a little bit this one, and a little bit this one, which you can see, right? So you can kind of see how this idea of attention practically shakes out after sort of the multiplication. You have these relatively small shifts that generally keep the same structure, but add a little bit of structure from other elements. That's essentially what's going on, right? So, I mean, yeah, that's the entire multi-headed masked self-attention sort of component. Does that make sense?
Yeah.
All right, cool. So there's also add norm. I talked about maybe a little too much in my previous meeting, the problem of vanishing gradients. So there are 2 things happen. Layer normalization happens, which is essentially normalization across the feature dimension so that the mean and variance of all features is the same. And that allows for, more consistent traversal. If you have a learning rate and you can kind of be oscillating, if everything's kind of normalized, it makes that work a little better. I know that this is not a topic that is exclusive to BERT. I believe layer normalization and this concept of normalizing on the feature dimension is very common in a variety of domains. So that happens. And then also residuals get added, which we also talked about. So, and I think that happens, let's see. Does that happen? Yeah, the residual gets added and then normalization happens. So, and that kind of makes sense, right? Because it'd be kind of weird to normalize and then add a value after, because it would kind of probably squash everything and mess everything up. So the residuals get added, and that is to help to compensate for vanishing gradients, and then normalization happens. Anyway, I'm going to try not to repeat myself too much, because when I presented last time, I repeated myself a lot. It was kind of it was difficult to listen to. Okay, so multi-headed attention happens, add normalization, and then yeah, I think this is just oh yeah. So this is a classic feed forward, right? So attention happens, add norm, feed forward, and then add norm again happens after this for the same reasons. But I think conceptually it's kind of cool, right? It almost reminded me of YOLO V1, how we had these convolutions that were isolated, and then you had a dense network that could do some sort of logic about separated regions. You can kind of at least I like to think of it this way. You can kind of think of this as sort of a similar thing, where you have a vector which is on the word has a word dimension, which the words are kind of isolated. There's some there's some relationship between the words, but they still remain fairly logically isolated. They remain mostly logically isolated because, as you recall, seeing multiple of these, normally the attention is just a diagonal with very small weights on the outside, right? So it's a small amount of context. But this feed forward network, which is dense, allows for some level of logic to happen densely, which I think is kind of similar to that idea that happens in YOLO. So I think that's kind of cool. So that's the attention mechanism in a nutshell. The output is the same exact size as the input. Conceptually, it's the same. You have the same dimensionality, but the content is now more context specific because of the multi-headed attention, as well as the feed forward system. Does that make sense? Is there anything that I should go over more?
No, sounds good.
All right, cool. So BERT. Now we talk about BERT and what it is, right? So BERT is essentially this just stacked. So there's BERT base, which was meant to compete with the original GPT. And then there's BERT large, which is just really freaking big. But essentially, it's just you take your embedding, you add attention, then you add attention, then you add attention, then you add attention, then you add attention, and you do it, in a repeated manner. So yeah, I mean that's the idea. So I think I could talk about this stuff, but I think really the best thing to now talk about is training, because really I just talked about attention is all you need and stuff, but the BERT paper specifically, the reason it was important is not because it revolutionized architecture. It mainly focused on novel ways of training. So transformers, and I think I have this understanding conceptually and completely, but I might not. We'll see. So the original attention is all you need was actually kind of quaint in its ambitions, which is kind of funny. It was just a way to make a translator between English to German. That was the goal, right? And because of that, the input sequence is not related at all with the output sequence. So you can consume the entire input sequence in one shot and then build the output sequence, and you don't have to worry about things like seeing information you're not supposed to, because there's no relationship really between the input and the output. Like, it's not like next word prediction, for instance. So the original transformer was bidirectional, and actually it's maybe a better way to think of it is omnidirectional. There's no, like, it can look at everywhere all the time whenever it wants. ChatGPT, the original one, was directional. So the objective of ChatGPT was to take this transformer idea, and I think it uses decoders instead of encoders. I'm not really super familiar with the architecture of GPT. But the idea is to take this attention thing and build a model that can predict the next word. So they use masking so that, for instance, it can't see the next word because if it's trying to train and it can see the next word and it's trying to predict the next word, it will trivially just return the next word, right? So as a result, GPT was actually directional. So part of the idea of BERT, the B is the bidirectionality. I think, what does it actually stand for? BERT, 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 BERT. Oh, I had it written somewhere, but I have so many notes. It's bidirectional something, whatever. So the way it gets this bidirectionality is through essentially changing the problem. Um, One of the things BERT wants to do is to do next word prediction, but it doesn't actually train on next word prediction. And it also wants to be able to do other stuff. So most of the magic happens in the training process. And there's really two things that it does. So one thing it does is sentence prediction. So instead of just giving it one sentence, one whole sentence, instead they have this special utility token, which is called a separator. And the model is provided two sentences separated by this utility token. My dog is cute. He likes playing. Whatever. And this is a wordlet, I think. So there's fun ways to do encoding, but regardless, it doesn't matter. Hold on, let me collect my thoughts because I don't want to. So the idea is, and it's actually, I wrote that article on self-supervision. It's actually remarkably similar, which I thought was kind of cool. The idea is you can give the model two sentences. You can give the model a sentence followed by the sentence that would follow it, or followed by a random sentence. And you can ask the model, do these sentences belong together or not? Right? And essentially, what you're kind of doing there is you're training a whole bunch of things in one shot. You're training context awareness, you're training a general understanding of grammar, you're training relationships between individual words and between sentences. You're training a whole lot, right? And the way you do that is by one of the outputs. So this NSP is next sentence prediction. There's one token on the output, which is specifically for next sentence prediction. So this would be, I guess, 1 if they belong together and 0 if they did not belong together, right? So that's one of the types of training it does. It does another thing as well, and it seems like actually it might do it at the same time, which is kind of interesting. I didn't read about that, but there's another thing it does simultaneously through the training process, which is masked word. This is word, not sentence. Masked word prediction. So 15% of the time, it replaces a word with this mask token. Well, actually, 15% of the time, it masks a word, and it does that 3 ways. One way is it replaces the word with a mask token. So it explicitly says, hey, you've been given this sentence, try to guess the token that belongs there. Another way it deals with the mask is you give it a sentence and you randomly tweak one of the words. So how might be garbage. So garbage are you doing today? And then the model has to identify that token is not good. This is what the token should be. And 10% of them are left intact. So R begins R. The model is tasked with predict the word, and it was right. So it just maintains the word R, right? So the reason for these 3 different strategies of masking is to entice generalizability. So because the mask token doesn't exist in the test set, it's, well, it doesn't exist in inference. So here, hold on. If we only use the mask, it would have learned only to predict the mask token. The model learns to correct it. Okay, yeah. So I think in terms of my conceptual understanding, the reason we use these three strategies is twofold. It seems the most intuitive to just use the mask, but if you just use the mask, it's not incredibly robust. It's not good at finding incongruities or inconsistencies. If it's given wrong data, it would probably be bad at dealing with it because it's never really seen wrong data before. And also, probably more importantly, by not using the mask token every time, it makes any word possibly something that the model has to correct. So if you say garbage, are mask doing today? If it only looked at mask tokens, it would try to predict you. But because a random word can be replaced with any other random word a very small amount of the time, it has to look at all the words to make sure they're accurate. So then instead of this becoming just, one thing, it has to look at all of these, make sure they're correct, and correct for any inconsistencies. So in terms of my understanding, that's really the big reason why you have these other strategies. I don't know if you have any questions about that. I'm
No, it
Gotcha.
seems, yeah.
Gotcha. Okay, cool. So, I mean, so yeah, that's essentially that's BERT, right? It takes a sequence, and the sequence has utility tokens that can divide it into two sequences, whatever, and then it tries to predict masked tokens with these guys over here, and it tries to predict next sentence prediction over here, and then that is the training of BERT by itself, right? That's the main idea of the foundational model that is BERT. And by doing that, you create a model that's pretty good at understanding language. Um, there are some minor architectural things. BERT does use pre-trained embeddings, I'm pretty sure, and I think it's word piece, but some other people said it didn't. I can't remember in the paper. Um, but it does use word embeddings. But BERT uses learned positional embeddings, which I didn't really read too much about. I assume it's kind of similar to the idea of functional embeddings, except it uses some type of information about the input space. The attention is all you need paper actually references learned embedding spaces, and they say they're practically similar to functional ones, which is why attention is all you need used functional ones. I think the reason BERT uses learned ones is because of this separator. You now have sentences that can end and then start a new sentence within a single input. So it makes sense not to use this functional encoding and instead kind of learn how to encode location based on the input space. Um, so, oh, and then they added the separator token, which I think is a novel utility, which allows for this next sentence prediction type of idea. So great, we have a model that's essentially useless, right? But you can add things to it to make it useful, and that is the power of BERT. So, uh, so there's a bunch of ways to fine tune BERT. I looked up a few of them, and I kind of looked for some general trends. So when you're doing classification, usually what happens is you have this output token, which is for next sentence prediction, um, and you attach um, a dense network to that, probably a fairly small one, and then you learn uh, you can learn labels from that. And I think that is the most common way to do multi-class classification or any classification, is to use a dense network attached to this sort of output token here. And then here's another example, right? So you
Wait,
have,
sorry. What sort of labels would we learn here?
so anything, right? That's kind of the power of BERT. So
Mm.
again, the reason BERT exists is to be a general language model that you can then
Mhm.
attach uh, things to fine tune for specific tasks. So this says is next, is not next, but is happy, is sad. Um,
Oh, in that sense, okay, yeah, I get
yeah,
it.
or like um, master student, PhD student, college or bachelor student, and high school student, right? I think it can be really broad. Pretty much any way you want to classify text, you in theory can use this to do it. Obviously to varying degrees of accuracy. So that's kind of a classic thing. I also saw people using it. What was it? I think it was efficient debt. That idea of having a convolutional backbone, extracting things into a neck, and then taking that neck and then feeding it through a dense head. I think that is also an idea in BERT because, as you might recall, in
No,
BERT,
so the neck itself. So yeah, you were referencing the pyramidal. Uh, I'm forgetting the names, but the neck was generally the entire procedure of like taking certain feature maps and running running sort of convolutions again, but in the opposite direction. That it was pyramid P and
yeah, something like that.
I'm forgetting. Yeah.
Yeah. So, as you might recall, all of these have the same shape, right? After the encoder block. And all of these have different levels of abstraction. So, I saw a quote from someone uh, early BERT layers learn more generic linguistic patterns. And it's kind of actually very similar to convolutions, where you have sort of general high level features in the beginning and then sort of lower level, more specific features at the end. So because BERT is, kind of this self similar thing that has various
There's the
embeddings throughout.
FPN, feature pyramid network. But
Yes.
the kind of like the what you were referencing, kind of like the efficient dent, the parts of the neck are both FPN backbone and path aggregation, so PANs, and they're sort of combined, and you can run multiple of them in a way. But yeah.
Yeah. So and I think there's probably a ton of things you can do, right? I think it's mostly a architecture agnostic series of approaches where you can use some type of neck, regardless of how it's structured, to extract these various hidden states. You might do one direction, you might do bidirection, you might do some other really. I remember in your YOLO paper, you had, or I can't remember if it was your latest YOLO presentation, but there are a ton of different necks that you can choose from with different architectures that do all sorts of fancy stuff. Um, but you can do things like that with BERT. And that's something that people do. And then you can also get kind of wild with it, right? I hadn't seen anything like this before. I'm not sure exactly what's going on, but there are sentences with separators, and then they apply a multi-layer perceptron to where the separator is. I assume these are fixed length regions that
I
are padded.
believe it might be for like classification of sentences
Yeah,
in a
yeah,
way that this to me looks like they're sort of predicting, okay, what the sort of, I don't know, what did the kind of like previous sentence do, I guess.
yeah, something like that. And it has some level of context awareness because the prediction for Y3 has information about Y1 because it was passed through BERT, and you have all these dense layers and self attention and all that jazz. So there's a lot of stuff you can do with BERT, which is kind of why it's cool. Um, and I'm kind of excited because I've been wanting to break into natural language processing, and BERT seems like it's designed to be, because it's really expensive to train BERT, right? Like BERT was like, multiple thousands of dollars, massive data sets, et cetera, et cetera. And also, BERT is really expensive to train. I looked it up as in terms of like its relationship with other models, and because of these masked tokens and all that stuff, you have to show it a lot of data for it to get signal out of it. Um, and I'm not super hip on the technicalities of that, but it's it seems like it's very expensive to train BERT. So the idea of BERT is you have this massive model that you can then add crap to. So that's kind of exciting. So I think one of the things I'm frustrated about right now in terms of reading is like I read a paper and it's like, wow, this is amazing, but I don't really have a conceptualization of where it lies in the current state of the art. Um, I think based on my brief research that BERT is a little passe. I think it was the state of the art maybe 4 years ago. I think it was 2018, and then it was probably still very relevant for the next or 5 years ago. It was still probably very relevant for like 2 or 3 years after that. But it seems like different models have sort of passed, like the various versions of ChatGPT. Google created BERT, and they also created this model Palm. There's also Claude and these other ones. But one of the things that's interesting about BERT is because it's a foundational model, it's kind of hard to compare it tit for tat with other models because a lot of these models are for like very specific things, whereas BERT can be generalized fairly easily to all sorts of stuff. So it's still something that people talk about, and I do think it's still something that people use, but it's not currently in vogue, I don't think. That was my understanding. So that's BERT in a nutshell.
Having dived a bit into YOLO, I feel like there's a lot of just kind of people think or kind of like get from these presentations that like those are specific elements, but a lot of the elements from what I was presenting were first presented as their individual networks.
Yeah.
So, for example, the feature pyramid network was actually FPN net. It was its own kind of like neural network. Then someone did a pan net, which built upon that. When basically YOLO took those two concepts and just merged it into their neural network, made a few additions, and called it YOLO V4, I believe, or YOLO V3, I think, one of these. So it's basically a lot of just the line between what is still an element and what is like its own neural network, I feel like is much more blurred than people think. It's like, oh, I'm using YOLO. It's like, yeah, but you're at the same time, you're basically using the Rep VGG, FPN, and all of these kind of neural networks, because it's just YOLO is at this point like YOLO V7 is just a glue of so many other kind of concepts borrowed from other networks.
Yeah.
But yeah.
And I suspect that natural language, I mean, it seems like currently all of natural language processing, at least for LLMs, is transformers. At least as far as I understand, it seems like the most it's like the ConvNet of visual, of like computer vision. It seems like so, and like BERT itself might not be super common, but this idea of stacking attention, I believe, is like I think ChatGPT, the original one, was instead of stacked encoders, it was stacked decoders, which is really interesting. And I believe you can stack both. I think there's probably a lot of crazy things you can do. Kind of the world's your oyster. So yeah, definitely the concepts within BERT are still very relevant. It seems like because they're transformers, and it kind of pioneered this idea of stacking. I think, or at least it was close to that timeline of when people were pioneering stacking. But yeah, BERT itself, like in terms of a model, I don't think is super used. But yeah, I'm not sure actually. I still need to look into it. But anyway, that was my TED Talk.
Yeah.
Hopefully a little better than the attention is all you need presentation.
No, it was very good.
Cool.
Looking, because I was thinking, so the next one would be my turn, right?
If you want. Yeah, and I think I do want a brief break. I took a lot of long breaks because I was moving and stuff. I'd like to get back into doing it more, but I'm also currently trying to do research on non-homogeneous data and how models relate with that. So I want to get at least some traction on that before I take over another paper, at least on the reading path.
We can do 1 week break because I think I'm gonna be quite tired next week as well. The issue is I'm working Sundays as well. It's middle of the week.
Oh, gotcha.
Because I'm doing this side gig of teaching kind of basic coding. But yeah, it takes up my Sundays. But yes, I believe we can do in like 2 weeks. That should be fine. But yeah, I was thinking, I recently met my friend from MIT, and he told me that like most of the research right now is in vision transformers. I was thinking of reading about vision transformers because we've done a lot of, and I feel like it might also clarify a bit of the NLP stuff. Because I feel like if we kind of understand how the attention works in an area that we understand better, or at least I feel like I understand vision, object detection kind of like a bit better, then yeah, I think that might also help. And also, yeah, if it's a hot topic, then it would be nice to have it.
Yeah, I think I agree. I think right now I'm at a point where like I definitely need to read more seminal papers, but I feel like I'm getting to the point where like I'm scratching the state of the art, but I'm just a few years behind. You know what I mean? And it might be kind of nice to at least sprinkle in some more cutting edge ideas. Because I'm also, maybe not immediately, but I would like to get into research at least a bit. So definitely reading more state of the art stuff I think would be useful to me as well. So, and I can't imagine Vanutha would complain, and I think she would be interested in that as well, because she's more on the computer vision side as well, right?
Yeah, and I feel like we've also can you hear me?
Yeah.
I also feel like we now have sort of